This session, which has two parts, will begin by having INAE young associates delivering their talks on a diverse set of topics, which will be followed by tea break, and then we'll have the 3-minute thesis presentations as the culmination of the competition which got introduced around a month back. To chair this session, I would like to invite Professor Bigyan Bandyopadhyay, visiting professor at IIT Jodhpur. Sir, may I request you to grace the stage, please? Professor Bandyopadhyay received his engineering degree in Electronics and Communication Engineering from the University of Calcutta, India in 1978, and a PhD in Electrical Engineering from IIT Delhi in India in 1986. In 1987, he joined the Systems and Control Engineering Group at IIT Bombay, India, as a faculty member, where he was a chair professor. In 1996, he was with the Lehrstuhl for Elektrisch Sternberg and Redoing RUB Bochum, Germany, as an Alexander von Humboldt Fellow. He was awarded Distinguished Visiting Faculty Fellow by the Royal Academy of Engineering, London in 2009 and 2012. Professor Bandyopadhyay is a Fellow of the INAE, National Academy of Sciences, and the Indian Academy of Sciences. He has 400 publications, which include monographs, book chapters, journal articles, and conference papers. He has guided 37 PhD theses at IIT Bombay. His research interests include the area of multivariate output feedback-based discrete dime sliding mode control, event-triggered sliding mode control, and nuclear reactor control. Professor Bandyopadhyay served as co-chairman of the International Organization Committee and as chairman of the Local Arrangements Committee for the IEEE ICIT Goa, India in 2000. He also served as one of the general chairs of IEEE ICIT Conference Mumbai, India in 2006. Professor Bandyopadhyay has served as general chair for IEEE International Workshop on VSSMC Mumbai 2012. He has also served as associate editor of IEEE Transaction on Industrial Electronics and IEEE ASME Transactions on Mechatronics. He is currently serving as associate editor of IET Control Theory and Applications. Professor Bandyopadhyay has been awarded the IEEE Distinguished Lecturer of IEEE IES Society in 2019. Professor Bandyopadhyay is an IEEE Fellow. Sir, may I request you to conduct this session and take the session forward.
Thank you. Hello. Thank you, Dr. Sankal, for this introduction. Good afternoon to you all. We will start our very interesting session, that presentation by INAE Young Associates, by 3 speakers we have today, and we will start one by one the presentation. The first presentation will be Dr. Swatantra Pratap Singh. He will speak on electroconductive surfaces and membranes for desalination and wastewater treatment. I will call upon Dr. Swatantra to come here to present the talk. Before starting, I'll just introduce him. Yeah, he has a lot of achievement, but I will briefly introduce him to the audience. He is an associate professor at IIT Bombay in Environmental Science and Engineering Department before joining IIT Bombay in December 2018. He was a postdoc scholar in Zuckerberg Institute of Water Resource and Ben Gurion University, Israel. He is an environmental engineer with training. Just a minute. Yes, he is an environmental engineer with training in pollution control by using state-of-the-art technologies. His current research interests are desalination and wastewater treatment by membranes and nanomaterials for environmental remediation. He has established an environmental nanotechnologies lab with state-of-art technologies for membrane technology, for desalination, and wastewater treatment with 20 group members, with the help of IIT-B and EACD department. At present, his group has 10 sponsored projects as lead PI, as a PI, and 5 as a co-PI in the area of environmental science and engineering. His group is developing sustainable technology which could be used in rural areas and future smart cities and help us manage our water resources, groundwater, and other natural resources. He has developed a key technology to fabricate the membranes for water purification and print graphene in situ in a single step. He is also a co-inventor in 6 patents and 3 provisional on membrane and laser-based graphene fabrication technique. He has 29 journal articles in high-impact journals such as ACS, Nano, Materials Today, Applied Materials and Interface, Carbon, Chemical Communication, and Journal of Membrane Science. He has also experience in the transport and remediation of organic polluants and nanotechnology and biodegradation, and 6 journal articles and 2 book chapters on the related field. Furthermore, during his tenure at IIT-B, different agencies have recognized his work, such as INAE Young Engineer Award 2020, European Membrane Society, and EMS Young Academics in ICCOM 2020, ICEES and ISEES Young Scientist Award in the recent times. So first of all, I congratulate him for his very outstanding work at IIT Bombay. And I also feel pride, it is my proud that, I am proud of it that I was also at IIT Bombay, and he is a young faculty. He might have joined recently at IIT Bombay a few years ago. So please start your talk.
Thank you, Professor Bandyopadhyay.
Yeah.
So
his title of the talk, I think, the electroconductive surfaces and membranes for desalination and wastewater treatment. Please start.
So good afternoon, everyone. Today I am going to talk about interesting journey about this electroconductive membranes and surfaces, especially based on laser-induced graphene. So, which was invented in 2014 in Rice University, USA by Professor James Tour, who is a leading material scientist of the world. And then that time in 2015-16, I moved my postdoctoral studies and to Israel, and we had a collaboration with him, and he asked us to investigate this laser-induced graphene application in membrane technology. So I will start with this material. Also, like recently, their group also invented one new materials called flash graphene. Basically, like it's methods, the laser-induced graphene or a flash graphene, where in a cheap way, or you can say like very low-cost surfaces or the powder we can fabricate. So mostly my talk is going to be on laser-induced graphene, but briefly I will also talk about flash graphene, which is a one method which was basically invented because of the invention of laser-induced graphene. Because laser-induced graphene, when Professor Toor lab and also my Israeli professors and also at IIT Bombay, when we were trying to see the mechanism how laser is converting a surface into a graphene surface, we were able to find something, and then we tried, and then we were able to convert different kind of plastic waste into graphene, but just by using flash. So just starting with the first, because I'm mainly focusing on the desalination and wastewater treatment. So membranes in desalination technology, it's not new. It started long before in 1960s when Sidney Loeb and another Indian scientist, they have invented RO membrane in University of California. But that time its use was not that much because of many other issues. The membranes has material related problem. Also the energy for RO or different kind of things was quite extensive. But especially if you see after 1990s, we have seen a revolution in material science, and after that also day by day, because of new kind of contaminants are coming into the picture, so water regulation also became strict. So also energy recovery units invented by different groups. So with this, it makes this membrane technology we can use for water and wastewater and desalination. And if you see like this membrane technology, especially the pressure-based system, we can get a wide variety of treatment option. For example, using microfiltration and ultrafiltration, we can have a pre-treatment. When we need high quality of water, we can go for nanofiltration and RO. So generally remember this membrane technology is not just our reverse osmosis membrane. We have other kind of membrane which can help us to get a very good kind of pre-treatment and also many places good quality of water. So if you see at present, the current rate of growth for membrane technology is huge. It's around 17%, which is actually coming from water recycling, reuse, which is based on membrane and also desalination. But the problem is with these membranes, they also their tendency to foul. And there are different kind of fouling we can see in this membrane when we are using for desalination or wastewater treatment. For example, we have colloidal fouling, we have organic fouling, we have scaling and biofouling. And out of this, the biofouling is the worst one, because here living microorganism can involve, and then what they do, like first they attach with the surfaces and then they start forming their colonies, and after different stages when they are fully grown, they can just go away and contaminate other places in the membrane. And the interesting, according to your environmental condition, this whole process can happen within few hours to few days. And this has created a lot of problems when we are running a very big plants. For example, in Israel, like they are pioneer in desalination technology, they are running 5 big desalination plant, and many times what happened, their whole plant got suffered because of these kind of biofouling problem, where within few hours, if pre-treatment is not proper and microorganisms are able to reach to the RO membrane, then they can block the whole surface. And these are some of the representative SEM or digital images which shows how severe this can be happen. And in many cases, we have to remove these, replace this RO module, which are quite expensive. So biofouling is reducing their life a lot. So it's showing overall potential, and at present, if you estimate the overall cost, additional cost, what we are putting in desalination or wastewater treatment because of biofouling, it's 30% extra. So what are the solution? The traditional solution is we can, after biofouling, we will try to use different kind of biocide or chlorine to clean these membranes. But what happened also, like if we are using RO membranes, which basically they are thin film composite, and they get damaged if you are using a lot of chlorine. So also the best thing, if you see, if we want to control this biofouling, we have to work on these initial stages of biofouling, where these microorganisms, they are attaching to the surface and then growing. So how we can do that? Either we can first inhibit the attachment, or we can kill the microorganism when they attach to the surface. So there are different sets of membranes now coming into the picture, where scientists are trying to modify membrane surfaces. They are trying to change the first by either doing a chemical modification or a physical modification. By that we are changing the property of the membrane, and by that way we are just trying to delay the initial attachment. Remember, it's very almost impossible to come up with a membrane which is going to be 100% foolproof of the biofouling. In their lifetime they will get biofouling, but our idea is to delay this process. And also, like, if we want to attach certain chemicals to the membrane which can kill the microorganism after attachment, for that also different kind of biocides such as antibiotics, antimicrobial peptides, or nanoparticles such as metal nanoparticle and graphene are being used to modify these surfaces. So our idea to use the graphene for membranes is come from those. And I hope most of you are aware what is graphene. So graphene is one of the allotrope of carbon. It's electrically and thermally conductive. It's light, and if you see, like, in recent time, in last 10 to 15 years, it's had shown its potential for environmental application. We have seen it can be used for antibacterial as a catalyst, for noble absorbent, and also electrodes for pollutant degradation and sensing. But if you see the most of our traditional systems by which we are fabricating graphene, powder, they are either mechanical cleavage or solution processing, or if we want a very high quality of surface, then we are going for chemical vapor deposition. In all, like, if you want to come up with surface, it's a multi-step process, lengthy, and also many of them are using very hazardous chemicals, which problem. So for that, there was a need for a method where we can fabricate graphene-based surfaces in a single step. So then it comes to this laser-induced graphene, which was invented in 2014, which it was also, like many other invention, it was accidental. When Professor Tour Lab's postdoctoral student, Dr. Lin, he was cutting a polyamide polymer with a normal CO2 laser cutter, they seen a black powder, and later when they have characterized, they have seen a characteristics peaks of graphene. So with this, they have published a Nature communication in late 2014, where they have shown in a single step how with normal laser, CO2 laser burning, we can convert a polyamide polymer into the graphene-based surfaces. So then he had contacted us to investigate for in membrane technology. So generally, like, remember our idea, as I have told you, the biggest problem in membrane is fouling. So our idea was to use for antibacterial and antibiofalling properties. Here these two terms are very confusing. You have to remember, when I am talking about antibiofalling, means I am just talking about to repel the microorganism, not kill the microorganism. Antibiofalling surfaces means that surface is not going to allow the microorganism to attach to the surface. Whereas when I am talking about antibacterial, means that surface will kill the microorganism. So don't mix up with this. So generally we want a surface which can just resist the biofouling. We are not interested to kill the microorganism. So in that case, we have tried to investigate the antibiofouling properties and antibacterial properties of this laser-induced graphene. And as you know, graphene is electrically conductive. So antibacterial properties we have investigated both with and without electricity. So what we have found, like without electricity, it has shown very good antibiofouling surfaces where microorganisms were not able to attach to the surfaces. When we were giving the electricity, they are also getting killed. So basically, the further researches concluded these laser-induced graphene, they have 3D structure where you can find a micro-size pores and nano-size fibers on the top, and which was the main reason of inhibition of these microorganisms, because they were not able to sit on these surfaces properly, and so they are not able to grow. which we have seen when we have crushed these surfaces. Then what we have seen, like a lot of biofouling growth, you can see when we have done the experiment with the crushed surfaces, we have seen growth on these surfaces, whereas normal surfaces there was almost no growth. We have tried many other things to investigate whether some chemical release or something, but most of the time our conclusion was this is mostly the texture based. Also, also one interesting thing what we have find, when we have started the experiment, these microorganisms, so generally we have done experiment with Pseudomonas aeruginosa, which is a rod-shaped bacteria, and their size was around 1.5 micrometer. But later on, some of the microorganisms, they get attached to on graphene surfaces, you can see, but they converted to a cocci or a circular surface. So we have seen this laser-induced graphene, when microorganism was trying to attach with the surface, they were not able to easily attach, so they have tried to change their shape to attach with these surfaces. So also when we have done electricity experiment, without electricity you can see we haven't find any toxicity of these graphene surfaces to microorganism. But when we have applied electricity, you can see with 2.5 volt in 9 hours we have seen 6 log removal, and which has shown with electricity this surface can be very lethal for the microorganism, but without electricity it's not killing, but this 3D texture can repel the microorganism. So it's a antibiofalling surface without electricity, and with electricity it's a antibacterial surface as well. So with this, the idea was like when this laser-induced graphene was invented, it was only making on a polyimide polymer, which is a very good class of thermally stable polymer. So the challenge was how we can convert these polymers to a membrane, because in membranes most common polymers are polysulfone or other kind of polysulfones and PVDF, and there are many, but polyimide was not in the list. So then there was a challenge how we can convert how we can make the laser-induced graphene on these membranes. For example, polyether sulfone, because polyether sulfone is highly used polymer. We are making different kind of ultrafiltration membranes, microfiltration membrane, and also they are basis for we use as a support layer for nanofiltration and RO membranes. So later when we try to investigate how these laser is converting polymer to the graphene, we have found out like with a proper laser setting, we can go for defocusing or multiple lensing, and we can convert any kind of carbonaceous surfaces into a graphene. Obviously, the qualities may differ. For example, polyimide in a single step laser burning, it's giving very good quality of laser-induced graphene, whereas certain materials like PVDF and other thing, you have to do multiple lensing, but still the quality is not matchable with the polyimide. But what we have seen with polyether sulfone, polysulfone class have many different polymers, but one of that polyether sulfone is very good, very nicely converting into the laser-induced graphene. And we have used different kind of ultrafiltration membranes. We have converted them to in a laser-induced graphene filters, and we have performed several sets of experiment in a flow-through manner. Also antibiofalling properties, all were equally good or even better, because these polyether sulfone, they have a lot of sulfur in the moiety, and when laser converting into the graphene, these graphenes are sulfur doped. So they have shown even better electrocatalytic property as compared to normal polyimide membrane. So with this, it has shown a path how in a single step we can convert these membranes, we can convert, make these filters, electroconductive filters, which is a graphene based filter which is electroconductive, and then we can utilize different kind of electroconductive properties to make a new generation of membrane. So here you can see we have published recently a very good review article where we have demonstrated what different kind of properties, the electrical properties we can harness, and then we can solve a different problem in membrane technology. It's starting from fouling to disinfection, and also we can degrade different kind of new emerging contaminant like pharmaceuticals, and also we can sense fouling because these surfaces are conductive. So just by their change in the electrical property, we can easily sense what or how much fouling is happen on the membranes. So with this, we have demonstrated several things in last 4 to 5 years. For example, recently we have demonstrated how these filters can kill a different kind of viruses, especially during COVID time. Now I don't have to tell you like what is the problems with the different kind of viruses, and this laser induced graphene have shown very good potential, where at different voltages we have demonstrated how effectively it can kill not only the bacteria, also the viruses. Also, as I have shown, like when we use these electric surfaces in a, we'll pass the current in a resistor mode, these are very excellent Joule heater. So to demonstrate this phenomena, we also have made a different kind of Joule heaters in a single step. We have tried to stack them to conserve the energy, and recently we have demonstrated by the stacking of these laser induced graphene filters, we can do a very effective desalination, both in presence of sunlight, and when sunlight is not available, that we can use the stored energy and run this system in a Joule heating mode, and we can generate a water. So this system can work in any kind of weather if we integrate with the solar power. So when solar light is available, then we can have, for example, in presence of sunlight, it will able to generate the water. When sunlight is not available, or you need an accelerated rate of water, we can go in a Joule heating mode. And what we have demonstrated, just by stacking of these surfaces, we can gain a multiple thing. For example, we can reduce the footprint. We can get almost 7 times higher water evaporation when we are just doing 3 layers of stacking, and also energy consumption was 3 times less as compared to the single stage. So, and this work is just recently published in SES Applied Nanomaterial, and also we have filed Indian patent on this. So it have shown like how these laser induced graphene filters, normal filters, I am not talking about the membranes till now, just these filters which was fabricated in a single step, which are low cost, we can use in a very effective for the desalination. When it comes to the membrane, as these membranes, if you are not aware, just let me explain, only top few micrometers are active layer. When we are burning these surfaces with the laser, what happening, it's destroying the top layer. In that case, for example, you are using an ultrafiltration membrane which pore size in is few hundred nanometer, but when we are burning that surfaces, it converting into a filters. So to convert into the membrane, we have to do a post modification. We have demonstrated, we have done several post modification, and by that we have come up with a different kind of membrane such as LIG PVA and LIG Geo, and both have demonstrated very good separation processes along with the antibiofalling properties. And what is we have demonstrated also, these membrane can effectively remove pharmaceuticals such as ciprofloxacin. So here you can see at different voltages we have effectively shown these membranes can remove different kind of pharmaceuticals. Also, these properties of graphene can be enhanced if we doped with a different kind of metal. For example, we have recently doped with a Maranglini phase titanium oxide, and we have shown enhanced property for killing as well as other catalytic properties for degradation. So if I can talk the last 5-6 years of progress, in last 4 years we have demonstrated these filters can be effectively converted into the membrane. Also we have shown like these, when we are doping with different kind of metals, its performance is improving. We can make a robust composite for different kind of application, starting for membranes or the sensors or even for supercapacitor in that. We have demonstrated its antiviral properties. we have shown how electroconductive surfaces is going to be a new generation membrane for desalination and wastewater treatment. Stacking can help us to reduce the energy demand and footprint, and also like there is another class of graphene which is basically inspired by this laser induced graphene. When we are burning that surface, so laser is giving almost 2200 to 3000 degrees of temperature, and the same thing we have tried to do with a normal electrical flash, where when we are burn that surface, these surfaces at in the flash, presence of flash, light flash, it's converted into the graphene. And also these we have demonstrated effectively how these surfaces can be effectively used for a sustainable use, because we are in a single step we are converting these surfaces into the graphene. And also all these surfaces they are we can utilize different kind of waste material also to convert into the laser induced graphene or a flash graphene. So we have we have licensed to this LIGC startup, which is a Israeli based startup, and also in this way we have demonstrated different kind of surfaces and a membrane can be made for environmental application. So in last, I would first acknowledge the students, IIT Bombay, national collaborators, international collaborators from Rice and Ben Gurion universities, the funding agencies, and in last the INAE as well as IIT Jodhpur for giving this opportunity to participate and interact with the young generation. Thank you.
Thank you. Thank you for this presentation. Now I will open the paper for discussion. Any question? Any question? Yes, please.
Hello, sir. You have told that we can convert any carbonaceous material into graphene, right?
Yes.
So can we convert biochar, which has high carbon component, to graphene?
You can, and for that laser induced graphene, better than laser induced graphene, you can find flash graphene is a better method. So you can convert that. Even if you just follow two of the publication, one in, I am also the co-author, where we have demonstrated how different kind of carbonaceous surfaces can convert into a laser induced graphene, and another paper which recently in 2020 published by Professor Toor, and also one paper where we have demonstrated how different kind of solid waste we can take and convert into the flash graphene. Right now the challenge is upscaling of flash graphene, where till now we are just making in kgs. So how we can make a bigger reactor, that is a challenge of more like a chemical engineering and electrical engineering problem. If we can able to upscale, this technology is going to reduce the overall cost of graphene, which will right now, for example, we are getting in almost 10,000 or more than 10,000 per ton of graphene, which can come to $700 or $800 per ton. So if just you follow those two articles, you will able to see like how you can convert biochar into the graphene.
Thank you, sir.
Is there any other question? Okay. If there is no other question, once again I thank Dr. Swatantra for this nice, relevant research work on new membrane technology, what I understand, and also the laser-induced that some filter which he has made that is very interesting and very relevant to the present context. So that is, we conclude the session. Now I am happy to present a memento to the speaker, Dr. Swatantra, on behalf of INAE SERB and IIT Jodhpur. I present a memento to Swatantra. life at microscale. I will briefly introduce him. He is presently an assistant professor in chemical engineering department at IIT Kanpur. He completed his PhD from Cornell University, where he worked on understanding fundamental properties of polymer nanoparticles composites. Subsequently, he did his postdoc at the University of Wisconsin-Madison, where he worked on active Janus particles in liquid crystals. Presently at IIT Kanpur, his group is focusing on investigating the motion of artificial swimmers such as self-propelled Genus Colloids and self-propelled emulsion droplets in complex surroundings. He is also the recipient of INAE Young Engineer Award in 2020. So please start here.
Hello. Hello. Okay. Thank you, Professor Bandyopadhyay, for the kind introduction. A very good afternoon to all of you. Okay. So before I begin, I would like to thank the organizers for inviting me to this young conclave. I'm extremely humbled and honored to be a part of it. So since one of the themes of this conclave is on futuristic technologies and healthcare, what I'm going to do now through this talk is to take you through an exciting world of artificial swimmers. Okay. I will not be going into the technical details of different aspects of artificial swimmers. Rather, I will try to give you an overview of what artificial swimmers are, what are the variety of artificial swimmers, what are some of the potential applications of these artificial swimmers in healthcare, and what are some state-of-the-art research developments in the area of artificial swimmers, and I'll also introduce some of our own group results while doing so. So when we think of swimmer, the first thing that comes in our mind, or the first image that pops in our mind, is something like this. He's Michael Phelps, by the way, who is one of the most celebrated athletes in the history of Olympics with around 28 medals in total. Okay. But our focus for the talk is not him, rather these biological micro swimmers. Now what is the difference? Difference is their size. When we think of Michael Phelps, we are talking about a size of the order of couple of meters. But when we think of these micro swimmers, these biological swimmers, we are considering a size of few micrometers, that is 10⁻⁶ meters. Now what is the consequence of this size difference? For that, the fundamentals of fluid mechanics suggest us that if we calculate a very popular non-dimensionalized number, that is Reynolds number, that tells us that if we calculate this Reynolds number, which essentially compares the ratio of inertia in the fluid flow, which is the tendency of the fluid to continue flowing, with respect to the viscosity of the fluid flow, which is the tendency of fluid to resist the motion. So if I calculate Reynolds number for these two swimmers, what we'll find out is that for Michael Phelps, Reynolds number is much greater than 1, whereas for these biological swimmers, the Reynolds number is much less than 1. So that tells us that the effect of viscosity in micro swimmers is very, very dominant. What is the effect of that? That effect is, it makes the swimming much more difficult. I mean, you can do a quick thought experiment that if I ask you to swim in honey instead of water, how difficult would that be? Correct? So, because of this low Reynolds number, we face a unique problem, which is the flow reversibility. Now, what happens in very low Reynolds number is that, if, for example, in this movie, I'm not sure if it's very clear or not, there is a mechanical flap which is moving forward and backward in a symmetric manner, right? So for the forward stroke, it is taking the fluid ahead with it, and while taking the backward stroke, it brings all the fluid back to the same location. And that is because of this low Reynolds number, because there is no inertia in the system. As a result of this, whenever this microorganism, they try to move through this repeated mechanical motion,
they are not able to displace the fluid in any net direction because the forward stroke and the backward stroke are symmetric. Alright. So because of this, the swimming in these length scales where the Reynolds number is very, very low is extremely difficult. So then the question is that how are they able to overcome this problem? So nature has come up with a solution to this problem in several years of evolution. So what I am showing here is some of the microorganisms which are performing swimming in their fluidic environments. The first one here is a Paramecium. If you look at its surface carefully, they have these hair-like structures which we call as cilia. Now the way the cilia works is that, for example, if it is taking the forward stroke like this, the backward stroke is not like this because that will be symmetric. And if this symmetric motion will not lead to any net displacement of the Paramecium. So if the forward stroke is like this, then the backward stroke is like this. So through this motion, they are able to break the symmetry in their mechanical stroke and they are able to propel themselves in the forward or backward direction. Euglena here, you can see, undergoes through a very complex shape deformation which is non-symmetric in nature, hence they are able to propel themselves. Similarly, bacteria, E. coli, which is a very commonly known bacteria, has a bundle of flagella attached to its body, and the way these bundles rotate is also to break the symmetry. Alright? And in doing so, they are also overcoming the problem of Brownian motion and micron length scale. And Brownian motion, we all know, it is a random displacement of a small particle or bioorganism because of the collisions of thermal collisions of the surrounding solvent molecules. Okay? So what these bioorganisms do is that they extract energy in terms of food from their surrounding. They perform asymmetric mechanical strokes and they are able to propel themselves. So how do we use this useful solution which the nature has provided us? So what scientists have done over the years is that they are trying to utilize the solution and prepare or synthesize something called artificial swimmers, which will be useful at micron length scale. So first I will introduce you to mechanical microswimmers. These are simple mechanical piece of equipment and they are driven by an external field. So we can use external magnetic field or external acoustic waves to drive these mechanical micromotors. Now remember, we need to break this symmetry because that is what is required to swim at very low Reynolds number. Now this breaking in asymmetry can be created using the shape asymmetry as well. So if their shape is asymmetric, so while they are performing some sort of motion, their mechanical strokes will also be asymmetric in nature. So scientists have shown that we can start with a very simple spherical particle and coat half side of that with something else that makes a Janus particle. That also breaks the symmetry. Or we can create something like this, which is very complicated in shape and it tries to mimic the shape of bacteria. Okay. So once we know how to synthesize these mechanical micromotors, if we try to look at their motion through external field, we can observe that in variety of these through videos I am trying to demonstrate that by the means of external field, which is typically a magnetic field, we can actually control their direction as well as we can navigate them to one place to the other place in a very, very precise manner. So this is all happening at micron length scale. Alright. And so whenever the field is on, they are able to translocate themselves, they are able to move, and whenever the field is off, they just stay put. Alright. So using this, scientists have over the years shown that we can actually perform some very useful tasks in the microscopic domain where humans cannot go. So one such domain is healthcare. And since these are micron length scale microswimmers, we can use them for potentially drug delivery and other biosensing applications. So this one what I am showing you here is that there is a small microparticle here, I don't know if you are able to see it, which is flowing against the blood flow direction. So blood is flowing from right to left and through external meal, this microparticle is being transported against the blood flow. And this is just a simple micro roller which is coated with some sort of protein. Once we know how to locate them to a different location, transport them to a different location, we can also selectively bind them to a targeted cell. For example, in this particular study, they showed that the same sort of micro rollers, they coated specifically with some sort of antibody, and they demonstrated that they bind selectively to cancerous cells, but they do not bind to the regular epithelial cells. Okay. Similarly, it was also shown that these micro swimmers can be used to pick up the cargo on their way while they are moving and then deliver it someplace else. Okay. So overall, you can see, and I hope you understand, that these micro swimmers have the potential to move in microscopic domains in a very effective manner. They can deliver the cargo to the desired location, and they can also selectively bind to the cancerous cells, which all demonstrate that they have a very useful potential application in healthcare. One of the most exciting works which I was able to find is on sperm bots. So I'll just play this movie quickly. So what we see here is a micro swimmer, a mechanical micro swimmer. It is capturing an inactive sperm cell, and then it transports it to an egg cell and delivers it there. Right? So this is a very unique application which was discovered by this group in 2015, and these are known as sperm bots. Right? Now, this is all good, but there is one problem with these micro swimmers, which is that since they are driven by external field, we use external magnetic field or external ultrasound waves. If we have more than one micro swimmers in the system, all of them have the tendency to move in the same direction, or all of them will perform in a very similar behavior. So that creates a problem, because if my goal is to perform 5 different tasks in the human body or in the microscopic domain, then these mechanical micromotors will not be able to do that. So one of the unique solutions which scientists have discovered over the last couple of decades is something called as self-propelled chemical micromotors. Right? So here, as the name suggests, they are self-propelled. So the driving force for these micromotors is inbuilt in these particles itself, in these motors themselves. Right? And we do not need to use any external field to drive them. Now there are 2 categories of self-propelled microswimmers. The first one is self-propelled colloids. Here we start with a building block which is typically a Janus particle or a Janus colloid. Now remember, in mechanical micromotors we need to use mechanical objects which were able to break the symmetry while they were trying to move. But here, since we do not use a magnetic field, we are relying on some sort of chemical process. Here we need to start with a particle which has asymmetry in their chemical composition. So we start with a Janus colloid, which is nothing but a particle which has more than one chemical functionality on its surface. So this is a typical representative of a Janus colloid, and the name Janus has been derived from Greek mythology, which is a 2-faced god, both good and evil, hence the name Janus to these particles as well. There are multiple ways to create Janus particles, but one of the ways which is very popular and which we also use in our lab is to use the physical vapor deposition or chemical vapor deposition. So we start with a monolayer of isotropic colloids. When I say isotropic colloids, these are particles which have same functionality all over its surface. So we create a monolayer of these particles. So this is a very nice monolayer of 5 micron silica particles which we prepared in our lab. And then through physical vapor deposition or CVD, we deposit metal vapor from the top. Now these metal vapor typically could be gold or platinum or palladium. And because of this shelf shadowing effect, only the top half of the hemispheres get coated and the bottom half remains uncoated, and we end up getting very nicely prepared silica platinum or silica gold Janus particles. We don't have to restrict ourselves to spherical Janus particles only. We can create variety of shapes of Janus particles, such as rod-shaped Janus particles or dimer Janus particles or even disc-shaped Janus particles. But how do we create motion in these self-propelled Janus particles? Right? We have Janus particles, how do they self-propel? So the idea is that, let's say we start with platinum silica Janus particle, a simple spherical Janus particle. If you put this particle in any medium and add hydrogen peroxide to it, hydrogen peroxide reacts on this platinum surface and undergoes this reaction. So silica is not undergoing that reaction, but platinum is. So the reaction is asymmetric. Hence, the reaction product's distribution is also asymmetric. That distribution, asymmetric distribution of reaction product, drives the surrounding fluid flow from silica to platinum because of the osmotic pressure they create. And since these systems are overall force free, we are not applying any external force of them. To balance the linear momentum, these particles drive themselves in the forward direction. So this mechanism is known as self-diffusophoresis because this is created by the gradient of reaction products. And we end up getting these very nicely moving Janus particles. And they represent in a way how bacteria would try to move, all of them performing independent motion in different directions. So we get these active Janus particles which are active. They do not require any external field and they are self-propelled. Similarly, we can create artificial droplets as well. So these are droplets of one immiscible fluid in another immiscible fluid, and they also perform very nice active motion. I will not go into the details of their propulsion mechanism, but very quickly, what we use is Marangoni Flow. So if we have a surface of water with black pepper spread on it, if we touch with our naked finger, nothing happens. But if we apply some soap and then touch it, we'll see a radial flow in the outward direction. And that is simply because when we are putting in some soap solution, we are adding surfactant to the system. Surfactant decreases the surface tension. So at the point where we have touched, surface tension has gone down, and outside the surface tension still remains high. That generates a flow which is known as Marangoni flow. Right? So over the years, scientists have started to look into how these microswimmers behave when we have variety of external stimuli. So when we have external flow, these particles are known to move against the flow direction. So we have flow from left to right, but we have these active particles which are moving from right to left. They can also move perpendicular to the flow direction, and that depends on how much asymmetry in their shape we have. And this is not new because this is shown already by biological swimmers. So if you look at sperm cells or bacteria, they already swim against the flow direction, which is yes, very useful for sperm cells when it leads to fertility, but is also very detrimental for us when it comes to bacteria because this property of bacteria is known to cause infections like UTI. Okay. Similarly, we can also look at the motion of active droplets in flow, and this is a very nice work which we recently published. Here we are maintaining a flow from right to left. So when the flow is 12 milliliter per hour, the droplet is migrating against the flow. When the flow is high, it starts to drift with the flow. And by very careful manipulation of these flow conditions, we demonstrated that we can trap the droplet between two particular locations. So you are still flowing the liquid, but the droplet is settling between two different points. We can also trap the droplet at a particular location while there is a constant flow. Right? We also demonstrated very recently that if we add a little bit of polymer to the surrounding, these droplets start to move in a very, very straight line motion. So without polymer, they are moving in a very random manner, but once we add polymer, they move in a very straight line motion. Now this is very useful because majority of the bodily fluids are complex in nature. They are not simple water. For example, mucus or blood, all of them have this complex behavior inbuilt. So once we add polymer, we demonstrate that they move in a very straight line motion. Yeah. They are also known to perform this collective motion. So when many of these active swimmers come together, they start to perform a very nice collective motion. They come together and they flow in a very unique pattern. And this is all because of the kind of flow field they generate in their surrounding, because they are propelling themselves by generating a flow field around themselves. And when they interact through this flow field, they are able to form these very nice patterns. And this is again very important for us because bacteria is known to perform these bacterial swarming before they form bacterial colonies. So if we understand how do these swimmers form, or they move collectively, we can probably gain more information about bacterial swimming and prevent formation of bacterial colonies as well. And very quickly towards the end, I am very excited about this particular slide because this comes from my group as well. So these active droplets are known to perform chemotaxis. Now what is chemotaxis? If we have a source of surfactant here, the study demonstrated that all the droplets move towards that. So they are able to sense the presence of a chemical and then they are able to move towards that. So all of these colorful lines are the trajectories of droplets moving towards the source. We showed very recently that these droplets also have the capability to deform themselves. So while they are moving, they are deforming their shape. Now what is the excitement? Excitement is that if we can somehow club this aspect and this aspect, we can probably create something like this. Now this is an artificial blood, this is a WBC, white blood cell, chasing bacteria in a pool of blood. So the spherical particles what we see is the platelets of the blood, the deforming shape is a white blood cell and that is chasing bacteria. So this is a real demonstration of WBC chasing a bacteria, and we need two things here. Sense the presence of bacteria and shape deformation. And these artificial droplets have demonstrated that they have the capability to sense the chemical gradient and deform their shape. So we believe potentially in very near future we can create something like this and synthesize an artificial WBC, which will be very useful in healthcare applications. Overall, I can only conclude that what we have explored so far all over the world is just this, which is the tip of the iceberg, and what needs to be done is this. There is a lot to be explored. With this, I would like to thank you all for your attention. I would like to thank the funding agencies, and I have taken the credit of all the hard work which some of my bright students have done. Biswa, Prateek and Karnika, I would like to thank their contribution as well.
Thank you for the presentation. Now I will open the talk for discussion. Some questions. Yes, please. Please start.
Okay, so as we have discussed, about the materials that we are using and their possible applications when we can use in the biological fluids as well as like in human body. So can these be also treated as a foreign bodies and body kind of rejects those, like the immunity as well? If
you are absolutely correct. Right now, majority of the swimmers which we have, they are foreign bodies, but there is an active research going on where we can create these swimmers using biodegradable material. So once we have that, we'll be very close to our objective that we can use them as potential drug delivery agents in body.
Yes.
Yes.
Yeah. So partly yes, we can coat some sort of polymer which is biodegradable, but the overall swimmer has to be degraded. So that's the goal, that whatever we inject in the body should be degradable in the end.
Yeah, problem with the nanoparticles are like they are also being utilized or being explored for various drug delivery and other applications. And the problem with the nanoparticles are like metallic or any other. As soon as they go inside the body, they comes into the body contact into the body fluid. The whole immune system triggers and they just flush it out.
I agree. So, which is why there is a lot of interest in developing polymer nanoparticles instead of using inorganic or metal nanoparticles, which are not that biodegradable. If we can create polymer nanoparticles, which using some sort of biodegradable polymer, that is the future.
And one more thing, when we talk about the permeability of these nanoparticles through cells, I mean for the drug delivery applications. So what people have seen over there, like when you have this surface pattern, Genus nanoparticle, and there people use hydrophobic and hydrophilic combination. And when you use 2:1 ratio of like hydrophobic to hydrophilic, there's something particular to that ratio that you have very good permeation and very nice cells are also healthy, and so something is there to that ratio. So similar kind of observation can be looked at macroscopic scale as well in your
I think definitely all we need to do is some sort of selective coating on the particle which creates that selective hydrophobic and hydrophobic effect, and once we have that, we will be able to permeate these through cells as well. But right now the majority of focus is to create a biodegradable artificial swimmers where we do not have to worry about the contamination in the body. Once we go there, and then these things can be taken care of. Yeah.
We can take one more question, please.
Sir, hello sir. So there is a self-propelled, there is a platinum and SiO2, but there is a unidirectional. How to movement in the some degree and how to rotate?
So at very short times, when the reaction just begins, the particles start to move in this direction, forward direction. But since these are micron size particles, remember, so they have the tendency to fluctuate because of the Brownian motion. So they rotate because of that, those fluctuations, and over time they will change their direction.
Okay.
So they begin in unidirectional motion, but at long times their motion becomes random. That is in fact one of the major challenges. If we can come up with protocol where we can restrict their rotation and keep them moving in the same direction, that will be a big, big achievement.
Okay, thank you.
Yeah.
If there is no other question, we'll close this talk, conclude the talk. Oh, yeah, there is one more question. Maybe this is the last question we can take.
Sir, I'm talking about the magnetic force counting.
Okay.
Sir, we are controlling the magnetic force from the outside. No, we are controlling the motion of the motion of that microswimmer by applying some magnetic forces.
Correct.
So, sir, how do we know that what kind of force we need to apply? Because, sir, there are different kind of materials available at the micro level. So, one thing is this: how do we know?
So typically, it is known that what material has what kind of magnetization properties, and so you will use those materials accordingly.
But, sir, there is surrounding also, sir.
There is what?
Surroundings, the material surrounding, sir.
So material surrounding is typically any fluid environment.
But sir, that surrounding is also like variable in the.
Surrounding will vary, but typically surroundings are not magnetized in nature, right? So they are simple fluids or bodily fluids. So we use magnetic field to just affect the particle itself, but not the surrounding. So irrespective of their surrounding, we can still use the magnetic field to navigate them.
But sir, at some point, if the force is like a little more or less, then.
So those kinds of adjustments have to be done, and those we do with repeated experiments and through control experiments, that the magnetic field should be such that it propels the particle only, but it is not adversely affecting your surrounding, which is your bodily fluid. So which is why it's not very easy to see these technologies right away in healthcare, right? There are a lot of control experiments have to be done, a lot of regulations have to be satisfied, then only they are brought to the market.
And sir, one more thing about your complete model. And sir, like we want to make that swimmer to swim.
Right.
And we want one more thing, that it can't, if we are making that swimmer inside some human body, then we want that swimmer can't affect in the negative sense that human body. So we have some requirements and some limitations. So what is the basic model, the design? Some few steps would be fine. So what is the basic model in order to think in that direction?
See, the fundamental idea is that whatever swimmer you create has to be biodegradable in the end. Right now, the focus is not on that. Right now, the focus is more on how do we gain more and more control on their motion. Once we understand how do we control their motion, the second step would be to come up with protocols and synthesize microswimmers using biodegradable material. Okay. Right now, we are not there yet. As I said, we have just explored the tip of the iceberg. A lot of more work has to be done before we can actually use these in applications. Okay.
Thank you, sir.
Okay. Thank you. Thank you, Dr. Rahul, for presenting this illuminating talk on artificial swimmers and the micro swimmers and their very nice applications also he talked. I hope the audience and I myself will be little knowledgeable about what is micro swimmers and artificial swimmers. And I wish him a very good success in future research. Thank you. Thank you very much. Now present a small memento to Dr. Rahul on behalf of INAE SERB and IIT Jodhpur. Late, but now I will call upon the third and the last speaker, Mr. Rakesh Gupta. He will talk on modeling and simulation of biological barriers and systems. I will briefly introduce him to the audience. He is from the research, he is a research scientist at TCS at Pune since 2013. He has completed his BTech and ME in chemical engineering from NIT Jaipur and IISc Bangalore respectively. His research interests are molecular simulation of soft matters, polymer, lipids, and protein, etc. The modeling of bio-nano interface and QSPR modeling. He has published 28 journal papers, 1 book chapter, and filed 28 patents in various geographies, out of which 8 patents have been granted. He has presented his work at several national and international conferences. He has received INAE Young Engineer Award in 2019 from INAE, Indian National Academy of Engineering, for his contribution in chemical engineering field. He is also a young associate of INAE. He is a member of Indian Institute of Chemical Engineers. He is also a winner of the TCS Young Scientist Award in 2020. He has served as a reviewer for various international journals like RSC, PCCP, Nanoscale, Journal of Physics, Chemistry, Journal of American Chemical Society, Journal of Molecular Modeling, and Molecular Simulation. Now I invite him to present the talk.
Thank you. Thank you, Professor. I hope I'm audible. First of all, I would like to thank the organizers for having me here. And I would also like to thank Dr. Rahul and Dr. Singh for making my job easy, because some of the things that I'm going to talk, I can borrow from their slides again and talk about. I'll be talking about a little bit about graphene and a little bit about on drug delivery aspect as well. So thank you to them. So with that, I'll start my talk, and I'll be talking about different kind of modeling and simulation techniques which can be utilized to model biological barriers and systems. Okay. This is not working. It's not working. Anyway. Say it like that. Connected it. Fine, I'll use this. Sorry for that. So this is the outline of my talk. First, I will introduce what is the biological barrier, right? Then what is the motivation? Like why modeling is necessary, or why models are important and why they are required. And I'll talk about one of those barriers, like skin barrier function, and like how you can model it. And I'll talk about some of the case studies. Case studies, I mean to say, how they have been utilized in real world problem. So these are some of work that we have done with our clients, and they have seen the models has seen the real world data, and how well they perform, how bad they perform, all those things I'll talk about. I'll touch upon one more barrier is intestinal barrier, and finally, if time permits, I'll talk about like how these techniques can be utilized for something like that COVID-19 detection methodology or development. So first part is, what is biological barrier? So nature has evolved us millions of years of evolution and created us, right? And during this evolution, we have developed so many of these barriers. For example, if you apply something on the skin, it doesn't go out inside, right? Even if you put water on the skin, it doesn't go inside. The reason is the skin is providing a barrier, which is some epithelial barrier. Similarly, if we eat something, we take drug, it is not like all the drug or whatever we eat directly goes to the stomach. It has to pass through the whole, your GI tract, it gets decomposed. And whatever drug that we take, not 100% reaches to the systematic circulation. Very few amount of it goes to the systematic circulation. The reason is there are a lot of barriers. Barriers could be a could be a cell barrier, it could be an enzymatic barrier, or it could be an immune barrier. So if I have to develop some strategies, like to deliver these drugs through either skin or through the oral route, I have to somehow engineer materials, right? And I have to test those materials. So testing, first, one can be done through experiments where you have the live tissues and you can do the testing. Second, based on the modeling. So before I move, can anyone tell me like how much time does it take for a drug to come in market? Just rough guess. Or some numbers, some years? Yeah. So typically number is between 8 to 12 years. And how much spending? A rough number? Millions or? So typically the numbers are like, it's order of some few billions, like it can take 1 to 1.5 billion to reach a drug to a market. So this is a very costly affair, right? And if I talk about personal care or healthcare industry, so the common link is animal. But there is a harsh reality is, animal testing is banned in various countries, including India. Europe was the first one to come up with these regulations. Any cosmetic product or any ingredient of the cosmetic product cannot be tested on animal. So what you have to do then? You have to rely on some of other methods like tissue engineering waste, artificial cells or artificial models of whether it's a skin or other tissues. So there are some products which are there in the market. But the problem is these products are like kind of monopoly. It's not like if it is in Europe, you can transport it to India and you can utilize it. So there's a restriction for that. Another part is, as we just talk about, like it is a very huge time taking. It's a very big pipeline. It takes almost 10 to 12 years, all the way from finding out a drug molecule to taking it to patient and then monitoring and all. It's a huge time consuming and a lot of money incentive process. And even after that, after spending so much of this, the data is like 90% of these drugs failed at some point of the time of the clinical trial. So it's a huge loss. If my drug is failing here in the initial stage of drug development, it's a good for me. I would be okay, I would be happy it's failed here. But if your drug is failing around after 8 or 10 years, it's a nightmare for a drug company, to be honest. So the whole idea here is, the thought process is, can we somehow bring in this modeling and simulation based techniques, or we can create these models so that at least the initial part where the most of the testing that we are interested in can be reduced. We cannot go away with this, but at least the initial part we can do. So with that, all this motivation, we started working on these models, creating these models. I'll be talking about only one tissue like skin, and mostly the skin barrier function today. We have developed for other things as well, but I'll be focusing mostly on the skin. So skin is a multi-layer organ, right? The top layer is called epidermis, which is providing the chemical barrier. As I explained earlier, like if you apply something on the skin, it's not like things goes inside the skin, because it is providing the barrier. The second layer, dermis, which is made up of collagen and all, it is providing with a mechanical stability or mechanical strength. So what happened as we age or because of environmental condition, this collagen degrades, and because of that the wrinkling happens. So that is so we look young because of our dermis. So we should thank our dermis. The third layer is hypodermis, which is made up of adipose tissues. So these are mostly the drug target, like you talk about insulin. So insulins are given in a subcutaneous space because they work like a deposit, like you just put the drug over there, it will slowly diffuse. So that is the third layer. So now based on the application, you can utilize any of these layers. So suppose I am interested in a cosmetic application, right? I would be interested in the top layer. Like if I apply something on the skin, whether it is going inside or not. If it is going, how much of it is going? How fast it is going? Whether it is in a therapeutic window or not. Right? All these questions has to be asked. Top layer of the skin, epidermis, if I zoom in this particular part, it looks like this way. So the top layer is called stratum corneum, which is having this brick and mortar kind of structure, where bricks are made up of proteins, which are corneocytes, and these blue parts are made up of lipids. And these lipids are in a multi-layer in nature. Now, in the first talk, we talk about the experimental part where we are talking about the macroscopic system. The second talk, we talk about the microscopic regime. Now, what I'm talking is the nanoscale regime. Each of these lipids having the length of order of nanometer, which is 10 to the power minus 9 meter. So the arrangement of these lipids will determine whether my skin is permeable or not. So the skin barrier function is responsible because of these lipid layer. And this is a very complex. It's not like there's a single kind of lipid. There are multiple kind of lipids and multiple type of class of these lipids are present. So, as I said earlier, like pharmaceutical is still, animal testing is not banned, and testing is also done on the animals. But there is a lot of difference between animal skin and the human skin. And the reason is the composition. As I talk, like these lipids, their arrangement is going to determine their barrier function. So the composition in human is totally different from the animal. So the kind of barrier properties that a human skin will have will be totally different in an animal. The kind of flux, if I apply something on the skin, the kind of flux or the kind of molecule, number of molecules which are passing through the skin in human skin will be totally different from that of animal. So you cannot directly rely on that part. As I said, like I will be talking about at a nanoscale physics and all, but any material you take, whether it's a biological material or non-biological material, it's a hierarchical in scale. It means the things at the nanoscale, like at the molecular scale, the way they are arranged, the way they are interacting with each other will determine their macroscopic properties. Just to give you a simple example, like why I am focusing more on this nanoscale and individual molecule and all. This is a simple molecule which is having a straight, there is no double bond, and just incorporation of one single double bond changes the property of the whole molecule. This particular molecule is like in a solid phase, like we have saturated fat like butter and other dairy products, whereas incorporation of just single double bond changes the property significantly. And these are like unsaturated fat, vegetables, oils and all, right? So think of this way, like similarly skin, we have different kind of ceramides and their arrangement, even change in a one single double bond is going to change their phases. One could be in like a saturated phase and one can be in a unsaturated phase. And because of that, you have different permeability of the skin. So the method that we use is called molecular dynamics. I'm not going to the much detail of like what is the whole method. This is itself is a field which has evolved over the many years. Putting it very simply, it is like you are solving Newton's equation of motion. So you have atoms, you have molecules which are interacting with each other, and they are interacting with based on some potential. So we know like Newton's second law, F is equal to mu, or change in the rate of momentum is equal to force, right? This force can be written as a derivative of negative of potential. Potential means interaction. Just to make it simple, suppose you have two charges which are separated by some distance r. We have studied this long back in school, right? The potential energy between them is k q1 q2 upon r. And if you take the derivative of it, and you get the force between them. On similar way, molecules do interact. The only thing is the potential function u, which is not so simple when we talk about these molecules, which is complicated. But overall idea is you have an equation of motion, solving the motion equation of motion, where molecules are interacting with each other with some potential. So how we develop this model? So here you see, we take these three different class of molecules, as I talked about, ceramide, fatty acid, and cholesterol. And we do these molecular simulations. And if my physics is correct, if these potentials are correct, they should form these multi-layer of the skin that we generally see in actual skin. And this is what we see, that these layers are formed, and then we do a lot of validation with the experiments, like experimental data, neutron reflection, all this kind of data. I'm not going into the each and every detail, like how these are validated. So once you have this model, how you can utilize this model? You can take these drug molecules, and we have taken these 3 drug molecules. One may ask why only these 3. The reason is we had the experimental data available for these 3 drug molecules. How much of the skin permeation, human skin permeation happened for these 3 drug molecules. So you take this model, you run those simulations, you see how these molecules are diffusing. So the properties that we are interested is, like, if I apply something, how much it is diffusing, or what is the diffusion coefficient of these molecule. And based on some mathematical formulation, we can get these diffusion coefficient. But it's not completed yet. We have just only talked about that lipid path, right? I have just only talked about this blue path. I have not talked about the whole Stratton conium path. So that's where the multi-scale things come to the picture. The property that we have got from this low-length scale, like diffusivity and partitioning, is faded into this FEM model. And then we solve this based on finite element framework. And what we get is, like, how much of these molecules which is applied on the top is going inside with the time. And that's how you see, like, how well, how off, or how good we can capture the transport of these molecules through the skin. So you see that some cases we are having a very good prediction, but in some cases we are off. There could be multiple reasons for that. Even in the experimental data, the formulation was a bit different. Here we talked about a formulation where we mostly had the water, these molecules are dissolved in water and all. But experiment, the formulation was a little bit complicated. So because of that, you have changes in the partitioning, and that's why we observe these changes. So if I had to summarize the whole modeling part, like how this model looks like is, this is the top layer of the skin, again brick and mortar, the model development part, model testing part where we see the diffusion, then multi-scale modeling where we do FEM, and finally we see how well or off we are from the experimental data. One thing is, since we are using this molecular simulation based techniques, these are computationally little intensive. It is not like this simulation can be done simple on a laptop. You need a dedicated server for that. So can we speed up these calculations, right? Can AI or ML help us here? And recently we showed, yes, indeed we can do that. So as I said, like in molecular dynamics simulation, we create this trajectory. Systems are solved and molecules are moving here and there. So it's like a time series data. So these can be treated as like a long short-term kind of trajectories, right? So what we do, we take the data that we have generated for various of these drug molecules. We take those data, we pass through these neural networks, and this neural network, and we predict what is the change in the free energy. Free energy is required to calculate the permeability of any drug through the skin. And recently we showed like this kind of things works, and indeed you can do this kind of calculation on a simple laptop, and the results are very good. Having said that, as I said, skin is providing a barrier. It's not easy to breach the skin, right? To breach the skin or to breach this barrier very selectively, you need some strategies. And these strategies are divided in two parts. One is called active method, other is a passive method, based on the application. Active method means you apply some either electric field or some external actives like current or ion flux or any of these. Passive means whatever the formulation that you have, right? You mix something in it. It could be some other molecule, it could be nanoparticles, nanomaterials, or lot of different solvents as well, right? Now, I'll talk about three or four use cases where first we have done those simulations, and later on those insights are utilized for a client work, where they have shared their data with us. We have worked on their data with our model, and we showed like how you can incorporate things in your formulation so that it could be a better product. So before I move to like modeling part, I just want to talk about like how experiments are done. So for mostly all the skin research, this is the particular setup. Skin French diffusion cell is used. Here what you do, you take a skin sample. Now skin sample could be of animal, if human, or some synthetic as well, depending upon what kind of application you are looking into. You put that sample here, and whatever the molecule of interest you put at the top, and with the time you see how much of these molecules are crossing, and you just analyze them, and you just plot how much of molecule cross with the time. So this is how typically experiments are performed. Now I talk about the permission answers. So permission answers are the molecule which are put in your formulation. So whenever you see any cosmetic formulation, right, you just see that how many number of component it has. Each of these components some of them are permission answers, because once you apply something on the skin, as we said, it's not going to go inside. You need these other molecules to do your job. So these molecules go and sit in the skin layer. They do some disturbance so that they make path for the molecule of interest, which is for the molecule of interest. So this particular work we have done with the Harvard, where the Professor Samir Mitra Gotri, they have done the experiment. So what they do, they take the skin, they do conductivity measurement for an intact skin and skin which is exposed to these permission answers. So there is a conductivity changes happens because of change in the skin structure, and they measure this enhancement ratio. Similar exercise we do, but with the model. We put this permission answer, how much disturbance they do to the skin barrier, and we see that whether we get the correlation or not. We could get like 80% of the molecules that we tested we are able to match we are able to find those correlation. Now, based on that, we have done one work with this cosmetic major, which is European cosmetic major. They had two molecules, A and B. Sorry, I cannot give you the name, unfortunately. And the problem with those two molecules are like when they are using in their formulation, they get stuck in the skin. They don't go in the deeper layer. So they wanted us to test this permission answer, which can increase their diffusion or the more the partitioning of these molecules. So we designed some of these permission answer for them, and we did this whole testing within 2 weeks, and we could show like within 2 to 3 weeks you can come up with the permission answer which can enhance your permission of your molecule of interest. I go to the second case, and here all of us has experience, right? Yeah, I'll just finish it. So all of us has experienced this, right? When we use a lot of hand sanitizer, right? We see that the skin is getting dried, right? What happens when we apply very high amount of this ethanol based formulation, like ethanol or some other alcohol based formulation? They extract the skin lipids, which is not good. So you are disturbing your barrier. So that's why here you see, once we have very high amount of ethanol, like 60-70%, it is coming out of it, which is not good. So when lockdown was there, so this particular company approached us. They wanted to use, so they were making this hand sanitizer, but they wanted to incorporate some more molecules in their hand sanitizer so that this extraction effect is reduced. So we again incorporated two particular component from mineral oil and the coconut oil, and we showed that incorporation of those components can reduce your extraction significantly. And later on they tested these in their labs. I'll come to the final part, one more use cases, that is testing of actual formulation. So again, this was done for a international corporation, where they had this complicated formulation, where they wanted to test a different composition, different pH, and different condition of other polymers and all. And that's where again this whole multi-scale modeling framework was utilized, and we could show them based on the pH and the formulation composition, you have a different skin uptake. And again, it was later on was confirmed by them. So again, this is a recent work that we just completed. Here we have worked on mostly on the subcutaneous injections, and here the most challenging part was like when you do this testing of injection, it is very difficult process, because each skin is different. Like it's not like the skin that we have is similar to the Caucasian skin or the Asian skin or the European skin. I'll just take 1 minute. So here what we have done, we have developed model for them, and we could show like whatever the things that you do through the experiment can capture from these models. And these models were developed, it's a 2 years of effort, but now these models are currently being utilized by the client for the design of their devices. So with that, I'll stop. I'll just talk about this particular slide, and I'll stop here. We have also, as I said, not only skin barrier, we also look into the intestinal barrier. Intestinal barrier, when we take oral drug, it has to pass through the GI tract and it reaches to the intestine. Again, there you have a cellular membrane kind of environment, and which provides a barrier. So again, you can model these barriers, and you can utilize, you can design different kind of nanomaterials of different shape, different size, different surface chemistry, and they can be utilized for the drug delivery application. I think with that, I'll stop, and I'll be happy to take any question. Thank you.
Thank you for the presentation. Now I will open the presentation to the audience for questions and answers. Yes, one question from the last row.
Hello. Sir, you have shown some diffusion. Hello.
Yes, yes.
You have shown some diffusion coefficient data and VMD plot. Hello.
Yeah.
You have shown some diffusion coefficient data and VMD plots. What is the trajectory of the VMD data?
Trajectories?
Yes. How many nanoseconds?
So those diffusion data are calculated from the umbrella sampling simulations, right? Each window of the umbrella samplings are run for almost 100 nanoseconds. And then you look at the autocorrelation functions, right?
Right.
Once the and you get this trajectories which are independent, right? And then you calculate those diffusion coefficient and take the independent and take the means and standard deviation and all those things. So it is sufficiently sampled.
What is the what is describing from the autocorrelation data? What you are trying to describe from the autocorrelation data?
Okay, so autocorrelation data is like, suppose you have run simulation for 100 nanosecond, right? Is it enough? Right?
Yeah, sufficient.
No,
yeah.
You can't say that.
Maybe 300 nanosecond or more than that.
No. So there is a procedure for that. There is a mathematical procedure. So you take the trajectory, you calculate any of property like area per lipid or something, and then you take the autocorrelation. Autocorrelation will tell you there will be two time scale. One is a shorter one is a longer one. The longer one time scale is going to tell you whether you have your data, your trajectory is decorrelated or not. So suppose you get the time constant, second time constant is order of suppose 10 nanosecond or 20 nanosecond. It means the 100 nanosecond trajectory you can divide into 5 different parts, and which can be taken as an independent trajectory. So 5 independent trajectories, so each of that you can get the mean and the standard deviation. just based on time scale, you cannot say like 100 nanosecond is enough, depend on the problem state.
Okay.
Yeah.
Okay, thank you.
Is there any other question? It looks there is no other question. So once again, thank you, Mr. Rakesh Gupta, for presenting this research on molecular simulation and also modeling of bio-nano interface. Very interesting, and I hope, wish him a very future career at TCS.
Thank you. Thank you.
Thank you. Thank you. So now I will present a memento to Mr. Rakesh Gupta on behalf of INAE SERB and IIT Jodhpur.
Thank you, sir. Thank you.
So we conclude the session. Now I think they will join for a tea or something. Yeah, he will announce, we'll end the session, technical part of it.
Okay. Thank you all for attending this session. I'll request the guests and faculty members to stay back in this room for refreshments, and the students can please proceed outside for refreshments in an orderly manner. Thank you.
Good evening, everyone. We will now be starting with the 3-minute thesis presentations, where research scholars from all over India will present their research work within 3 minutes. We have a panel of expert jury comprising of Professor Bijnan Bandyopadhyay, Professor Bhagwati Prasad Kashyap, and Dr. Vidya Sarveswaran of IIT Jodhpur, and Dr. Swatantra Pratap Singh of IIT Bombay, Dr. Rahul Mangal of IIT Kanpur, and Mr. Rakesh Gupta of TCS to evaluate the presentations. A few rules. I'll display the PPTs already shared with me. Every participant will get only 3 minutes to present. I'll keep a timer and I'll intimate you when 30 seconds are left. And you'll get a mic and a pointer. So can we start now? The first one is Bikash Patnaik. You can start. Please start.
A very good evening to one and all, distinguished professors and dignitaries and my fellow colleagues. I am Bikash Patnaik, currently pursuing PhD in the Department of Mechanical Engineering, IIT Jodhpur. I am going to present before you on my topic, heat transfer enhancement during droplet evaporation from heated high temperature surface, a machine learning based study. So, So if we will move on to the nuclear industries or the industries with microelectronics or those industries that incorporates high heat fluxes, what issue we face like that the forced convection technique doesn't help that much to extract the heat from the surface. So two-phase or phase change heat transfer mechanisms are being implemented nowadays in order to extract heat from the surfaces. Droplet evaporation is going to be a very interesting aspect in order to extract the heat from the surface. So what basically happens that when we put on a droplet over surface in order to extract heat, the droplet impinges at a particular area and it starts engulfing the heat from that location and it evaporates if the surface is maintained at a quite higher temperature. Normally, what happens that when the droplet is impinged or imparted on a heated surface, it evaporates on the principle of constant contact area or constant contact angle. But this limits the approach towards analyzing the actual trend of how the heat transfer is taking place from the surface. So what I have done here is I have developed a machine learning based image processing interface that can detect the IR camera images, that is the non-intrusive technique implemented to extract the images from the droplet evaporation. And basing on the principle of the CME's network and neural network, we have developed this interface. This interface, as you can see here, that it can track or engulf the droplet over here, and we can select the exact area basing on which I can determine the area of the exact droplet through which I can calculate the heat transfer enhancement and how heat is being transferred from the surface. So here, as I can see that from these interfaces, I have implemented some of the geometric figures, and I am getting an accuracy within a range of plus minus 0.6% of error. So basing on this interface, I was able to extract the exact area of how the droplet is being impinged, such as in the application of cooling of turbine blades, cooling of turbine blades and cooling of any metallurgical plates. And based on that, I have found out the exact trajectory of the area, how the heat transfer is taking place by the droplet. That gives us an exact trend how we can enhance the heat transfer coefficient from the surface during the process. Thank you for having a patient listening to me. Have a good day.
The next one is Keyur. Please start.
Good evening, everyone. My name is Keyur Kansara. I am a PhD student in the Energy Conversion and Storage Research Lab here at IIT Jodhpur. Today, I am going to present about phase change materials, a promising alternative for the spacecraft thermal control management. Yeah. So the unprecedented pace of mankind in the exploration of the universe has set new challenges in front of engineers, which makes the spacecraft thermal control management even more reliable and highly precise in order to get a highly efficient systems. Now here I have shown an exploded view of the satellite payload. So this is one of the working electronic component inside this satellite payload, as you can see here. Now, the several critical subsystems of the satellite payloads works on a repeated transient duty cycles, meaning that they will generate a significant amount of heat during a shorter period of duty cycle, and during which it requires a highly reluctant and precise thermal management system. So in order to control the temperature of these components that I have shown here, we need to have some sort of system which can work on a repeated transient duty cycles. Now, if I talk about the thermal control challenges which we face in the space, which are not available in the terrestrial environment, are the hostile space environments, meaning that the cold deep space is available at 4 Kelvin, the rapidly changing illumination conditions, harsh heating in space re-entry phases, and one of the major issues that we face is the elimination of convection due to the high vacuum condition in space. So, accounting all of these challenges, we need to design a system that can work efficiently. So for that, phase change materials, the latent heat energy storage based materials, which can work or store the energy during this on period in the satellite payload, and it can reject the heat during the off period in the satellites. So the baseline condition for this is that, let's say I have shown here the payload component, the electronic component, and this is the radiator surface which is exposed to the space exterior, which is at 4 Kelvin temperature. So now let's say when this payload component is generating or dissipating the high heat, during that time, let's say if we are not using any energy storage materials, then this heat dissipation will be instantaneous. Now rather, by storing the energy, what we can do is, the heat we can store for a certain period of time, and then we can reject this heat when there is no external radiation on the radiator surface. But the major issue with using this phase change material is the low thermal conductivity, which can increase the high resistance passed through these materials. So in order to increase the thermal conductivity of this PCM, what we can do is we can use nanomaterials, expanded graphites, and encapsulation techniques, and many other more, or we can use the heat transfer enhancement techniques such as fin and heat pipes in order to do so. Thank you very much.
The next is Miraj.
Good evening, everyone. My name is Miraj Ahmed and I am a PhD scholar in the Department of Mechanical Engineering, IIT Jodhpur. And today I am going to present my work on the topic portable water sip-up by use and throw solution for the safe drinking water. As we all know that our planet is covered by 70% of the water, but only 2.5% of is fresh water. So there is an urgent need of having an affordable, clean drinking water, especially in the developing countries. So if we talk about India's market, there are so many water filters available in the market, but either they are very costly or energy intensive. So to find a solution for this, we have introduced a device known as a G filter. It is made up of locally available material at the Jodhpur, but there is a problem in that G filter that it is not portable. So for that, we have introduced another device that is known as a sip-up, and that is the working model of that sip-up. What we have to do, we have to just replace the cap of any commercially available bottle, and when a person sucks through the top of this particular bottle, he will get the clean water. Now talking about how this particular device has been made, we have used 3 local materials. The first one is the local clay that is available in Jodhpur, that is the Raital clay. It is salty in nature. The second one is the sawdust which is available freely in the carpenter shop, and it is acting as a pore forming agent. And the third one is the marble slurry. It is basically freely available and contains calcium carbonate. So we have mixed all of them in a definite proportion. We have prepared a green mold by using a mold that we have prepared to make a uniform dimension in all the way, and after that it has been kept in open atmosphere for 2 days for drying, and after that it has been baked at 850 degrees Celsius in the muffle furnace. Now talking about the dimension of this particular product, it weighs around 68 grams and having the porosity of 43%. Now if I talk about the mechanism, so basically when the raw water passes through this ceramic water filter, it passes through the pores available in it, and the contaminants get trapped in it. It also contains calcium carbonate, which is act as a adsorption site, so contaminants get absorbed on its surface. We have also performed some lab experiment. We have got the average pore diameter of around 8 nanometer, and it is having the E. coli removal efficiency of nearly 99%. We have also performed some compressive tests, and we are getting enough rupture resistance for it. And we have also performed some electrokinetic parameter to judge the pH, turbidity and conductivity for this, and we have found that we are getting sufficient result, very close to the WHO results. So this is a basic solution for getting a safe drinking water, especially for the lower economical portion of the society. And so this particular device is affordable. This is portable ceramic water filter. It conforms to WHO standards, and most importantly, it is an income source for the pottery, and it can be used anywhere while trekking and traveling. So this is all from my side. Thank you.
The next is Sarwar Singh.
Okay, good evening everyone. My name is Sarwar Singh and I am a PhD scholar in Department of Electrical Engineering. So today's topic is AI-enabled identification of organic honey using surface enhanced Raman spectroscopy. Next. So may I please draw your attention towards the first picture of my slide, that there are three honey samples in the picture, and by looking at them we cannot distinguish that which one is organic and which one is not. So one is organic and the other two are having a trace amount of pesticide or other contaminants in them, but it is very difficult to identify that, and I am developing a technology which can do just that. So to distinguish the organic honey from other types of honey, such as raw, filtered, flavored or any kind of processed honey, I am developing the technology which is called AI-enabled surface enhanced Raman spectroscopy. So even if we produce honey at our homes, then it can still not be organic, because the pesticides which we use in the soil can eventually end up in the honey traveling through the bees, because the nectar contains the pesticides. So here is the schematic of the experimental setup which I am doing. So there is a laser source. I am shining the laser on the sample, and then the scattered laser light goes to the spectrometer and then ultimately to the detector. So this generates Raman spectral data. So if for conventional Raman spectroscopy the signal is very low, So, but the nano sensing platform which I am developing, it has a nano dimensional features. So this is the surface of my nano sensing chip. What it does that it enhances the weak Raman signal multifold. So this enhancement is so strong that it can go up to 10 to the power 9 to 10 to the power 10 times also. So this enables us for the trace level molecular detection. So after I have developed the Raman spectra, I can further complement it using artificial intelligence data processing, because even if I am having an enhanced data, it can still look similar for different kind of honeys. So what I am doing is that I am using AI algorithms. In this one I have used k-means algorithm. So the similar looking data can be distinguished using this algorithms, so that I can distinguish the organic honey from the contaminated one. So in a nutshell, I am developing the technology which has a nano sensing chip complemented by AI enabled technology, so that I can distinguish the organic honey from different kind of other samples, so that the society can be benefited, particular the food industry. Thank you.
Neha Prasad.
Are you starting? Yeah, good evening everyone. My name is Neha Prasad and I'm a PhD scholar in IoT and applications at IIT Jodhpur. My research area deals with real-time structural health monitoring of large structures using feature-based IVE. So often we use the term smart in the context of cities, transportation, homes, etc. But do we really know the meaning of smart? It's an acronym which stands for self-monitoring analysis and reporting technologies. Any infrastructure which has both monitoring as well as analytical capability can be termed as smart infrastructure. However, like to bring this into reality, we also need to measure the health of these infrastructures. Structural health monitoring is an important criteria to keep track of the structural damages to avoid any kind of disastrous changes. It's similar to human health measurement where we have different vital parameters like blood pressure, blood oxygen level, saturation level, etc. Similarly, in SHM, we have cracks, surface deformation, stress and strain, and vibration. So particularly in this study, we focus on the vibration analysis of large structures such as bridges and wind turbine. So to do this, we have two technologies, contact-based and non-contact-based technologies. So the contact-based involves sensors such as accelerometer and laser displacement sensors, which are deployed on the structure itself. And then we identify the displacement of these structures as well as the frequency at which the movement is happening. But installation of these sensors at a height of 70 to 100 meters is difficult, as well as they are prone to more environmental effects, and therefore it's a challenging task. So to reduce this or to avoid this kind of condition, we have non-contact based technologies such as digital image correlation, DIC. It uses the concept of cameras. So what we do, we deploy the cameras at a distance from the structure in such a way that it takes the full field of the structural moment, and then the DIC converts the pixel level displacement into structural displacement, as well as DIC performs the subset based correlation on the artificial patterns which are pasted on the structure itself. But the computation time is high and it cannot be implemented in real time. Therefore, in the current study, we enhance the DIC technique to be used in real time, as well as we give the user privilege to identify vibration of multiple regions present in the large structure simultaneously by the concept of parallel computation. Additionally, instead of focusing on the subset area, we use strongest point, which are identified automatically by the algorithm, which are uniquely present on the structure itself. So this reduces the time computation. Hence, the algorithm was demonstrated on a 2 megawatt wind turbine and a height of 65 meters, where the obtained results were in good agreement with the natural frequency of 0.42 hertz. Thank you so much.
Datta.
Can I start? Good evening all. My name is Akshay Datta. I'm a third year MTech PhD student at Department of Metallurgical and Materials Engineering. And my research area is design of multifunctional high entropy alloys by metastability engineering. So I will start a bit discussion with on conventional alloys. So the design strategy for the conventional alloys is that a primary element is selected based on the main property requirement of the application based as per demand of the structural, aerospace and automotive industries. And secondary elements are added to them in order to further enhance the performance. So since the conventional design strategy focuses only on the corners and the edges of the phase diagram, it leads to the confinement of the available design space, by virtue of which the design of materials satisfying only a single property profile is possible. And this gives rise to an analogy to the conventional alloys, which is single material for single application. But if we go to high entropy alloy design strategy, which has been proposed by Brian Kenter and JWA in 2004, so this strategy shifted the focus from the corners and the edges to the center of the phase diagram. And by virtue of which it provided abundant design space, and the materials materials satisfying different property profiles can be possible. So this gives rise to another analogy, that is a single material for multiple applications. Now, since if we see the two important terms that has been coined out back in 2016 and 2020, that is metastability engineering and microstructural flexibility. So according to those concepts, the phase stability in high entropy alloys can be made sensitive to the alloy chemistry, by virtue of which the gamma phase stability can be manipulated in such a way that multiple deformation modes such as transformation induced plasticity and twinning induced plasticity can be activated during plastic straining, by virtue of which the gamma phase will transform into epsilon phase, which will increase the work hardenability of the material at the end and provide excellent mechanical properties. And the microstructural flexibility concept gives rise to another term, that is reverse martensitic transformation, which is the exact concept for this shape memory effect that is observed in this material. And one important concept that I want to coin out here is that since the design of this material has been done with choosing the most cost-friendly elements, so the overall production cost for this material will be low in comparison to conventional alloys if we compare to the performance to price ratio. And the strengthening of the structural, aerospace and automotive sectors can be done by Making in India initiative. And the reduction in the total production cost is emerging demand of this today's Industry 4.0 era. So with this, I thank you all for your keen listening. Thank you very much.
Abhijit.
Hello, I am Abhijit. I am here to get your attention to lead free perovskites. Hello, I am Abhijit. I am here to get your attention to lead free perovskites as a materials for sustainable future in energy consumption application. Next. So you might have heard about the lead-based perovskites, because which has taken the photovoltaics by storm, and it has equaled the champion performance of silicon photovoltaics. No doubt, in last decade, the research and utility of lead-based perovskite has been skyrocketed. But do we have idea that how great threat it poses before us? The key element of perovskite is a lead, which is neurotoxic, nephrotoxic, and cardiovascular ecotoxicant. WHO has documented that there is no safe dose limit exists for lead, and it is even more dangerous than combined effect of chemicals of concern. So statistical data says that PV technology is going to utilize 1,000 tons of lead per year in Europe alone in the future. So it is a wake-up call that to realize that it is not a potential threat but an actual threat, and it is high time to look for PV-free perovskites. So focusing on this, we come up with the prospective solutions to rule out the need of lead in perovskites. I am talking about double perovskites. So double perovskites can be created in various ways by cationic transmutation, vacancy introduction, and charge disproportionation. Initially, I undertook the work of cation ordered double perovskites, where cations are arranged in orderly manner, where I studied 27 different materials, out of which 17 came out to be semiconductors. That means that they can be potential substitute for the lead-based perovskite. One of them was this CS2 AuBiCl6. It showed very appropriate or suitable electronic and optical properties. Therefore, we subjected it for the further device simulation, and it showed 22% of efficiency, which is comparable to champion silicon photovoltaics. Obviously, these predicted 27 materials, their stability is of paramount importance. So initially we investigated the thermodynamical and structural aspect of the materials, and thankfully all are evaluated to be synthesizable in a lab. So this year-long work of conceptualizing and executing the work on these 27 materials has resulted in a publication. My second approach is a vacuum-sorted double perovskite, where we create a vacancy of one cation but maintain the order. So this particular arrangement allows us to replace the tin, to replace lead by tin, and the distinctive arrangement of atom vacancy and oxidation state gives us the robust structure. So in conclusion, I have studied 30 materials, out of which 20 came out to be semiconductors, which can be used for single and tandem junction solar cells. Some of them, like CS2, UBA, CS6, have showed thermoelectric potential. This sustainable class can rescue us from the complex correlation of grate and threat of lead and mitigate the severity of solutions. Yes, there are some issues associated with these materials, but they hold even greater promise. Thank you.
Ghansham.
By day motivated to discover new methods of generating and storing the energy. You can see in the first Raguene plot, lithium-ion battery have higher energy as well as power density. So it is the best option for energy storage purpose. But due to the higher cost and unavailability of lithium-ion, may rise the concern through the availability of lithium-ion batteries. So here, being a metallurgical student, we find some such type of material which is earth abundant. So you can see in the first bar graph, aluminum is the third most abundant metal in the planet, and India has 5th largest bauxite reserves in the world. Second, it should be a cost effective. So you can see in the second bar graph, aluminum cost is 10 times lesser than lithium. Also, in terms of capacity, its volumetric capacity is 4 times higher than the aluminum, and in terms of gravimetric capacity, it almost touches to the lithium. So actually aluminum is also a very promising metal because it's a recyclable also. So due to the sustainability, it is very good for us. Actually, some researchers are already worked into the aluminum ion battery, but that cycle life does not go more than 100 cycles. So here we are comes with our new approach, aluminum intermetallic battery. We are using aluminum as an anode, nickel foam as a cathode. So during discharging, aluminum is oxidized in aluminum +3 and make intermetallic with nickel. And during charging, it can break the intermetallic and come with the pure aluminum. So we are also using the ionic liquid here, which is itself an ionic compound of aluminum ion, who is helpful to make the aluminum nickel intermetallic. So our battery material, it's proof our battery material is environment friendly, earth abundant, non-flammable, and it's good for cleaner and greener tomorrow. Thank you.
Vaishnavi. Vaishnavi Kali.
Very good evening to honorable judges and all my dear friends. I am Vaishnavi Kale, student of MTech Structural Engineering from NIT Raipur. In developing countries like India, infrastructure development plays a very important role, especially in transportation sector, as it contributes around 5.5% to the nation's GDP. If you talk about infrastructures and transportation sector, cable suspension bridges are iconic in its own way. These bridges can span as long as few kilometers without interrupting the waterway beneath. So these bridges, these are the iconic bridges, and in early 1800s, we see the modern cable suspension bridges were emerging in western part of globe. Today, in countries like China, Turkey, US, the longest cable suspension bridges are there. But the irony is, still in India, no such cable suspension bridge for vehicular traffic is designed by Indian designers. So, idea behind choosing the topic analysis and design of cable suspension bridge for vehicular traffic as my research topic was to motivate the youth and young designers of India to work on and implement such structures in our country. In my research, I have analyzed and designed a cable suspension bridge for vehicular traffic with incorporation of the Indian codes. For analysis, I have used softwares like SAP 2000 and STAD Pro, along with a parametric study for 3 different components, that is, one is for pylon height, second is for slab thickness, and third is for anchorage distance. The key outcomes of parametric study revealed that the pylon height above the deck surface of ratio corresponding to span by 6 to 7 is the most appropriate for the desired results. And the slab thickness of 300 mm is suitable for a 150-meter long bridge to cater all the serviceability criteria. Also, the anchorage distance with ratio of span by 2 to span by 3 is more suitable for all kind of cable suspension bridges. Thank you so much.
Sarthak Pipri.
Hello.
In this era of high inflation, the rising rates of steel, concrete, and other construction materials has emptied the pocket of the contractors. In this era, it is very important to make the project economical and get the optimum out of it. So for this, we need to make the project economical. The project management team is trying its best to make the project economical by applying its management techniques. But it is not enough. The designer of the project plays a very important role in the economy of the project. So, as a bridge designer, it is my duty to design the structure as economical as possible and make it sustainable. So, for this, the results of our assumptions should be closest to the what actually the structure behaves in the field. So, for this, I have chosen the FEM method of analysis for my analysis of the box cutter bridge. So for this, I've done the convergence study in the FEM model, and I've done the convergence study, and by decreasing the size of the elements, decreasing the size of the elements, and I've taken it as a benchmark results till I get the converse result. Then I prepared a Grillage model, which is usually used in industries. FEM models can't be used in industries that frequently because it gives the accurate results, but it is a very lengthy process and it is time consuming, and it involves lot of memories.
So I've tried the different grid sizes and matched the grid size of and matched the results of the grillless model with the FEM model, and found out that this graph that at a certain grid size we can match the results of the grid to the FEM model. So here I have analyzed the spans of 25 meter, 30 meter, 35 meter, 40 meter, and 45 meter, and done the analysis. So here we can see in this graph that the results of grillage and FEM are accurately matching at a certain grid size. So for a certain span, we can use the certain grid size element. Thank you.
Aryan. Aryan Kanojia. Not here. Anchal Mishra.
Good afternoon, all. There are many people in the world so hungry that even God cannot appear to them in any form except bread. And this was quoted by the father of our nation, Mahatma Gandhi. So now, let me talk to you about some data regarding to hunger. So around 823 million people they go to bed without having any kind of meal. Around 50 million people in 49 countries are teetering on an average of acute famine. Now, after 2019, the number of people who are facing severe food insecurities has surged from 136 million to 336 million. Now, this is what I have talked about the problem. The problem is the hunger. And what must be the repercussion, or what must be the alternative for that, or what we must do? Basically, the only way through which we can conquer famine or the food hunger is through increasing crop productivity. And how we can manage that is by giving the crops what they demand for. That is the micronutrient present in the soil, and especially nitrogen. But for that purpose, farmers have inclined toward increasing the use of chemical fertilizers, which has basically led to bearing of soil, or the soil has become so barren, and even the microflora has diminished very badly. So basically, we are facing three challenges over here. First challenge is to increase the crop productivity. Second challenge is to increase the microflora or to sustain the microflora. And the third is to dependency of chemical fertilizer should be that less that we don't have to look at that. In my present research, what we are doing is basically we are isolating root nodules bacteria from the legume plants. Okay, and what are these bacteria? These are the bacteria which fix atmospheric nitrogen into a usable form of nitrogen. Okay, so basically we isolate those bacteria, okay, and then we culture the pure colonies, and after that we do some kind of PGPR test, that is plant growth promoting activities, and then with the help of phylogenetic trees we characterize which kind of bacteria it is. We prepared a bioconsortia or a bioinoculum, and then we put it on other variety of crops so that we can see what is the effect. And basically what we have observed when we are putting a kind of bioconsortia or bioinoculum, the biomass of the new crop has increased very much. Now, so what is the meaning of all this? Basically, this research is very challenging and informative about the current scenario of hunger. So we can over here replace the chemical fertilizer with the bioinoculum or biofertilizers. So that could be a different approach or a different criteria to remove chemical fertilizers from the soil and would make our world a sustainable place to live in. Thank you so much.
Hello. Can any one of you sitting here smash their mobile phone on the floor? Well, the answer is no, I know. But what if I say, is any answer for that? So, I know the answer is no only. But what if I say your mobile phone will bounce back to your hand like a ball? Will you still be able to resist yourself not to throw it in the floor? Definitely not. It would be a game for you then, like a basketball. The situation is same as you are sitting on a chair and you suddenly fall on the floor. It will definitely hurt you. But what if you bounce back to the chair itself? Wouldn't it be interesting if such a material used in constructing big buildings and bridges? Heavy earthquake and plane hijacks won't be able to collapse big buildings. Heavy trucks won't be able to fail the bridges. Millions of lives will be saved. Yes, we get the victory. But how to continue this bouncing process forever? Ultimately, it has to stop somewhere. But we have to make it live forever. Well, my research aims to achieve that. Before understanding how it can be done, we'll just see the background. Whenever stresses are applied on the material, a cluster of atoms move together to form a shear band. This material is bulk metallic glass. So, to understand the situation, we'll just see, we just can go to our school days. During our lunch time, we all must be scattered everywhere in the classroom, like the atoms in bulk metallic glass. After our lunch, we decided to play tug of war. For that, we'll divide ourselves into two groups. One is here and one is here. So if stresses are exceeded by this group, this whole group of children will fall in a line. And this line will be called shear band. If shear band moves from one end to the other end of the material, catastrophic failure takes place. And due to that, we will have to lose the bouncing tendency of the material. If somehow we introduce an obstacle or a barrier in front of the losing party, this party will not easily move from one end to the other end, and thus we will go to the victory side. In my research, I have introduced a second phase or the barrier in front of the losing party or in front of the shear band basically, by heating the material till a certain temperature such that I can get the molten form, cooled it slowly, holded it for some time, and then just cool it rapidly. By that process, second phase is introduced in the material, and the second phase hinders the propagation of shear band. This is same as you must have seen zipper. It can easily move from one end to the other end. But if one link in the chain damages, this zipper cannot move from one end to the other. So the same purpose is served by the second phase here, in the stopping of shear band propagation. So now shear band is stopped, catastrophic failure has stopped, and this bouncing process will live forever. So now, not only we are a step closer to construct big buildings and bridges, but we have a material that promises us to keep us and our loved ones safe at homes and well traveled. Thank you.
Meenakshi Mishra. Meenakshi Mishra. G. Neeraj.
Good evening, one and all. My name is Neeraj Chaudhary. I'm from Mechanical Department, BTech final year Mechanical Engineering. We all know the on-screen person, Richard Feynman, called father of nanotechnology. He said he's the only person who promising the nanotechnology future in 1950s. Yes, he said there is plenty of space at the bottom for the nanomaterials. He gave the promising future, and we didn't believe that. In 20th centuries, the scientists said about nanoparticles. In history says that 20th century, but history was wrong. Yeah, in our ancient times, like in 4th century also, Lyricoscope in British Museum, also it made up of nanomaterials. 4th century and 17th century steel swords, all are from examples of nanomaterials. So it's not a new topic. But Richard Feynman then introduced after we promised the future. These are classified into 0, 1, 2, 3 dimensionals. 0-dimensional spheres and 1-dimensional nanotubes, 2-dimensionals are height and breadth, 3 dimensions are crystals, self-assembled crystals. Yes. Okay, characterization techniques are, there are two approaches for nanoparticles. The top-down approach and bottom-up approach, top-up approach and bottom-down approach. And the characterization techniques are tests, the technical, same spectroscopic and microscopic. Spectroscopic FTIR, UV visible, and microscopic are SEM-TEM, scanning electron microscopy and technical electron microscopic. What is how nanoparticles, why are they using for medical departments? Because nanoparticles, example, nanoparticles have a large surface area, very large surface area. So if we dope or something, it will be more efficient and more effective. So nanomaterials have such benefits. It benefits without side effects. We can cure cancer treatment and used in also the HIV treatment. Thank you so much for the opportunity.
Khushali.
Good evening all. My name is Khushali Joshi and I am pursuing Masters in Physics at Pandit Dindayal Energy University, Gandhinagar, Gujarat. Okay, so my topic is hydrogen generation. So first of all, our overwhelming reliance on fossil fuels has a significant impact on our economy as well as in environment. The use of fossil fuel in excess pollutes the air and hastens global warming. As a result, finding a substitute of fossil fuel, which is a long term, is crucial. Hydrogen gas is the cleanest and safest option. There are lots of several methods for generate hydrogen, but I used water electrolysis because water electrolysis is a viable method to generate hydrogen in a sustainable way, as we all know that water is renewable and plentiful. Water is plentiful, and I also know that it's not true, but we can generate hydrogen from wastewater also and seawater also. Okay, so you can see this figure. I generated hydrogen in my lab and store it in plastic bag. I used these two electrodes, and for that I made a plastic container, which I just took only one plastic container, and so it's no need of any kind of hydrogen generator. We can generate it at home also. So these are my electrodes. So in order to create low-cost prototype, stainless steel electrodes were employed. But what happened? It worked very well as a cathode, but as anode, it encountered corrosion problem. So I replaced it with this carbon fiber composite electrode, which gives a stable performance, but not gave better efficiency. So I used MiS2 as a catalyst, which has a very good quality like high density active sites for hydrogen evolution reaction and high strength and stiffness. So from this graph, we can conclude that carbon fiber plus MiS2 electrode gives the best performance among all electrodes. This is the photovoltaic and electrochemical coupling. So photoelectrochemical water splitting is break water molecules into directly hydrogen and oxygen using solar light and photoelectrochemical materials. Thank you.
Maitri.
Greetings to all the jury members. I am Maitri Patel, final year BTech student. I am presenting on synthesis of geopolymer using waste walnut shell. Basically, what is geopolymer? Geopolymer are inorganic, typically ceramic aluminosilicate forming long-range covalently bonded non-crystalline networks. It is inorganic aluminosilicate polymers that form solid ceramic-like material at near ambient temperature. And walnut shell-based geopolymer have low thermal conductivity, which makes this geopolymer good candidate for insulation material. The walnut shell contains lignin, cellulose, and hemicellulose, which improves the mechanical strength of the geopolymer. We know that there is a lot of problem regarding the global warming. So a major issue of global warming is emission of CO2. And another major issue is agriculture waste and white pollution. So how to overcome this? My project is based on blending of this PET granules and waste walnut shell to form a mixed geopolymer. My methodology is like I'm using fly ash, metakaolin, walnut shell, and solid activators, which are prepared 24 hours prior before mixing process. And then the process is done and geopolymer is formed. We found that the tensile strength of the walnut-based geopolymer is more than another material geopolymer. And applications are, it is used for construction materials, pavements, fire resistance. It is also used in a railway and many more things. Thank you.
Dharmik.
Hello, good evening to everyone. This is Dharmik Joshi, BTech Chemical final year student. My title is the production of industrial fuel by pyrolysis of waste sludge and e-waste. The both material are the totally non-usable for the every chemical and pharmaceutical industry. As we can see that we have two images in the right hand side. First one is the Zetropa sludge and the second one is the PCB. The both material is the raw material for our industrial fuel. Zetropa is the low cost biodiesel feedstock with good properties and the PCB is the printed circuit board. Zetropa sludge is totally non-usable for the every chemical industry. Our main product is the industrial fuel and the biochar. As we can see that we have one graph in the left hand side, which is the result of TGA of our raw material, which shows the weight loss percentage with respect to temperature. This slide is our problem overview. First point is our problem statement, that nowadays the many industries use the Zetropa to produce the biofuel. After the statin oil remaining, the Zetropa sludge is dumped on the land. So the waste Zetropa is the totally non-usable for the every industry. But we obtain the industrial fuel by the utilization of the Zetropa sludge and with some ratio of the e-waste. For that purpose, we designed the pyrolysis method to obtain the industrial fuel at the very high temperature around the 600 to 700 degrees Celsius. And the industrial application of the industrial oil is basically used in the industry and the automotive application. This is our basic flow diagram which we have to follow, and the all equipment we design which we mention here. First one is the pyrolyzer, heating chamber, condenser, and the storage net. This is our TGA result data which we have to use to design this all equipment which we want. Last, the application of our product, that the industrial fuel is mostly used in the field of biochemical, pharmaceutical industry, and the fuel compound. Biochar is used as the adsorbent in the adsorption process. Thank you.
Satyam Dalmia, Rajkiran,
Hello, greetings everyone. This is Raj Kiran, a research scholar in mechanical department from IIT Jodhpur. So before I give a peek into my topic, I just want to elaborate, give the terminology initially, that is dynamic scaling. It is just like a litmus test where you develop a similarity solution between your system that you are developing and the actual or original model. So this mathematical model, it gives the relation between your system and the original one. So in that way, you can change the parameters of your system so that the original conditions are preserved. So my study is basically, it means that the study of forces on the flexible wings, which are scaled. And that is why the title, Aerodynamic Investigation of Dynamically Scaled Flexible Flapping Wings. And the motive of this study is to develop and design a highly agile and efficient micro-air vehicle. That is an acronym for MAV, that which you will see in the next slide. So what are MAVs? MAVs are basically the smaller dimension drones. And why are we developing this? Because of their small size, they can be used in various applications like defense-related, surveillance, and rescue operations. So, and how are we going to develop it? So, this has the answer, like whenever humans have tough decisions to make, we look towards nature. And we all know nature has the solution for us. And here, basically, we are concentrating or developing the MAVs inspired from natural flyers. And these natural flyers involves small birds and insects. So the insects, why, one can say why insects? Because insects have, these natural flyers have evolved over the centuries, and they have very effective and efficient flight mechanisms. So then how do we develop it? So these flight mechanisms of insects, they have very complex phenomena. So to understand this phenomena, we have developed a flapping mechanism model, which can generate any flapping kinematics of any arbitrary insect, so that the aerodynamic forces, the forces that are generated by those wings, are studied using this flapping model. So this model is actuated by some 3 actuators, and so different actuators, and this can generate any kind of insect mechanism. So the aerodynamic data and the force data that we are obtaining from this model, these are used to develop the wings of MAVs. And these MAVs, as you can see here in the image, there is a test rig that is developed in the lab, which is used for testing these developed MAVs. And the flexibility, as this is a fluid structure interaction problem, so even the flexibility effects are taken into account, and that is used for modeling the MAV. Thank you.
Srinivas. Srinivas.
Good evening all. My name is Srinivas and I am a third year PhD student here in Mechanical Engineering in IIT Jodhpur. So I will be presenting on the topic experimental and numerical investigation of film cooling in supersonic flows. So what is a supersonic flow? Any fluid that is flowing with a speed greater than that of speed of sound in that particular medium, we call the fluid to be flowing with a supersonic flow. So what is the motivation of my topic? So for any country, a fighter aircraft or a spacecraft is an important technology that that needs to be there equipped with the nation because of a threat from the other nations or something. But only a handful of countries have it. Why? Because there are certain technological limitations that are associated with this complex technology. And through my research, I will be looking into one of the aspect of that technology limitation, that is the cooling method. So we all know that this spacecraft to move with high speeds, the enough thrust should be generated. So with that requirement of enormous thrust, the temperature levels are also very high. So with that comes the engines are often run at very high temperatures that it will often melt the wall surfaces. So there comes the cooling part. So already there are enough cooling methods which have been used and exhausted over the years. So now researchers are looking into new cooling methods, and one of the technique is the film cooling technique. In this technique, what we have is we'll inject a secondary fluid at much lesser temperature. Suppose a supersonic flow coming at a higher temperature of around 2000 Kelvin or something, we'll inject a secondary fluid at 300 Kelvin or something. So it will form a thermal barrier in between the wall surface and the supersonic flow, which will carry away the most of the heat and protect the wall surface. The secondary fluid can be either gas or liquid. So my objectives would be to check whether the formation of film in the supersonic flow, and once that is known, we will optimize the secondary injection parameters like the diameter of the secondary injection and all. So I'll be performing certain experiments on subscale model of gas turbine blades that are used in fighter jets, obviously because I can't use the actual size of the gas turbines or spacecraft. So and the numerical studies that we have performed on ANSYS software, that is a mechanical software that is used to simulate fluid flows. And in that we have found that with the gaseous film injection itself, there is a reduction of 60% of the temperature of the wall surface. So as I said, liquids have a higher heat carrying capacity. So when the liquid is injected as secondary fluid, it can perform better. So to validate the numerical studies, we have performed some of the experimental studies. And the figure 2 that you can see, that is a supersonic wind tunnel present in our lab. And those are the injectors through which we will inject the secondary fluid, mainly water. So we'll analyze the film formation and all, and then we'll be implementing it in the practical applications like gas turbine blades or the spacecraft exit diffuser. Thank you.
Gargi.
Good evening, everyone. My name is Gargi Kumar. I'm a research scholar from the Department of Electrical Engineering. Today, I'm going to present my work, and the title of the work is Eco-Friendly Multifunctional Flexible Devices with Natural Materials for Sustainable Electronics. First of all, I will briefly discuss the motivation behind my work. As we know that human dependency on electronic equipments is increased day by day, which consequently increase the demand of newer technology after every few months. Because of that, the lifespan of devices are getting shorter, and these devices are discarded or disposed to the environment. But most of these devices are fabricated by using some non-degradable and toxic materials, so a huge amount of electronic waste is generated. And we know that India is the third largest electronic waste producer after China and USA, and all these three countries together have produced almost 54 metric tons of electronic waste. Then we can imagine how this issue becomes very critical and challenging to our environment, also our human health. So people are trying to introduce a new area that is called biodegradable electronics, where we're trying to develop organic devices by using some biodegradable and natural materials which have similar functions like MOSFET technology, and we can reduce the
impact of EOS on the environment in an effective way. And apart from eco-friendliness, the multifunctionality is one of the critical issue. If we want to work more than one function on a particular device, there's a lot of hybrid integration and a lot of circuit complexity is there. So my aim is to develop such kind of devices which have multifunctional properties by using natural materials so that I can reduce the circuit complexity in a significant way. Also, I can reduce the production of e-waste. Here I'm showing some biodegradable materials which can be used to develop high-performance organic transistor. Instead of using silicon wafer, my aim is to develop these devices on some unconventional substrate like paper and cloth so that roll-to-roll printing is possible, which can lead a cost-effective large area fabrications. And apart from substrate, we can also explore some natural protein-based materials like chicken egg albumin, silk fibrin, cellulose, and gelatin to use as a dielectric material, which can be used in different multifunctional properties like biodegradable, like skin-like electronics, and e-textile applications. Here I'm showing one of my fabricated devices, which is fabricated on a flexible substrate by using a natural material. And this device this device can perform two functions together. One is the light sensing, and another one is the humidity sensing. Then we can understand that this area of technology has huge possibility in the future generation, and by using this kind of materials with multifunctional properties, this area can lead a path towards the development of high-performance, eco-friendly, flexible electronics for sustainable future. Thank you.
Kohli Sumaja.
Good evening, everyone. I'm Kohli Sumaja, PhD scholar from Department of Civil and Infrastructure Engineering, IIT Jodhpur. So today I'm going to present on sand dune migration and mitigation studies using subsonic wind tunnel. So before I go into the technicalities, let me give you a glimpse of what the actual problem is that has motivated us to venture into this area. So many of us have been in Jodhpur or Rajasthan. So whenever a sandstorm comes, we try to take a shelter. We try to go into a building so that we could protect ourselves from the sandstorms. But at the end of the day, we see sand in our hair or in our bag, wherever. So imagine yourself being protected by the four walls and still ending up in sand. But imagine the position of the infrastructure that is in desert. So it has no protection. So, and you can see these infrastructure are not any silly things. They are of national high importance. National highways, railways, and our India's largest renewable energy sector, pride, solar power plant, largest solar power plant. All these are being buried by the sand. So when this happens, it reduces their performance. So realizing this, we have taken the objective of the study to propose some stabilization techniques to mitigate this sand migration. When we say propose some stabilization techniques, we need to first understand what is the sand characterization, what is the properties of this sand. Firstly, we'll collect the data from various parts of Rajasthan. The desert in Rajasthan is 4.5% area of total India. So imagine how much we could develop if we implement this technology. So once the characterization is done, we'll try to understand the migration patterns. What is the migration patterns? How are they moving with respect to various wind? So for that, we have taken a wind tunnel. We are currently in procurement of that, wherein we will try to understand the migration patterns. Once the migration patterns are learned, we try to analyze it using ANSYS Fluent also. Once all this are done, we know this is the characterization, this is the properties. Now we'll see the various stabilization techniques. When I say stabilization techniques, I have to see something that is sustainable, right? So one of the things is that Rajasthan is house for rich in mineral deposits like limestone, sandstone. But the thing that is not known is it is having there is large amounts of limestone slurry that is being deposited like on roadside waste as roadside waste. So what if I could use this as stabilization for the sandstone, like the sand migration? So that is the idea that has come behind. And once this happens, we could actually, once this sand stabilization is done, we could improve this infrastructure, we could improve their performance also, and then at the end, we are improving the development. So I think at the end, we are giving a sustainable future for arid regions, mostly desert regions, which is a regional problem. So that's a wrap for my project, which I think concludes for the current theme of sustainable technologies. Thank you.
Ram Avatar.
Myself, Raman, and I am a PhD scholar in Department of Physics. Today I will talk about how cold plasma can be used for battery durability and how it is useful for sustainable development. So next slide, please. So air pollution is one of the top 5 environmental risks.
Prince. Prince Kumar Rai.
Good evening, everyone. My name is Prince Kumar Rai, PhD scholar in Department of Mechanical Engineering, working under the supervision of Dr. Ankur Gupta. Today, I am here for 3-minute thesis presentation on topic, fabrication of pulse electrode formed metallic microtube of various applications. Electroforming is unconventional manufacturing process which can Electroforming is unconventional manufacturing process which can be defined as the production or reproduction of any article by electrodeposition. So principle behind electroforming is electrodeposition upon a mandrel or mold that is also known as cathode. that is subsequently separated from the deposits. So basically the separated part or electro-deposited part is known as electroformed part. In this work, we aim to produce miniaturized product of various shape and sizes using this electroforming process, using this in-house pulse electroforming setup. The setup includes function generator and oscilloscope, which is used for providing pulse waveform instead of direct current waveform. And we have used power supply to give rotational movement to the cathode during the electrodeposition process. And using this in-house pulse electroforming setup, we have fabricated some metallic microtube of copper and copper graphene oxide of 1 mm internal diameter and having wall thickness of 20 to 80 micron. And on this microtube, we have fabricated zinc oxide nanowires above and inside the microtube. And this microtube has been utilized for the photocatalytic degradation of textile wastewater. And another application is like the wastewater coming out from textile industries. So we have utilized photocatalytic degradation method, and we have chosen methyl orange and methylene blue aqua solution of these dyes and performed in under sunlight. And from the UV vis result, you can see that in 120 and 135 minutes respectively, the water get decolorized. Another application of this superhydrophobic electroform microtube in the field of like fluidic transportation devices, miniaturized devices like microfluidic devices or biomedical devices, or in the field of micro heat exchanger. So our aim is to make this as received superhydrophilic microtube to convert them into superhydrophobic microtube so that it could not get absorbed water droplet or any liquid when we flow inside the tube. So from figure 6, you can see that the water contact angle has been changed from 57 to 156 degree of from hydrophilic to super when we converted as received copper microtube from hydrophilic nature to superhydrophobic. And the another image is showing like when water jet impinging the surface, it gets spread out throughout the surface in case of superhydrophilic. And in another case, when the tube is in superhydrophobic in nature, water jet impinge and reflected back in same direction. Thank you.
Ashwini.
by an amount almost twice than that of the as-built condition. But after nitriding, the hardness becomes
concept here that we are continuously providing the electricity to this aging treatment and nitrating treatment. But after aging, we find that for the aged specimen, the coefficient of friction as compared to the as-built specimen is reduced by an amount of 30%. And after nitrating, this decrement in the coefficient of friction is by an amount of nearly about 50%. And similarly, the wear rate of the aged specimen is reduced by an amount of 60%. That is a big number as compared to the as-built specimen. And after nitrating, it is further reduced by an amount of 90% as compared to the as-built specimen. So now, one thing is clear that instead of using the as-built specimen, we will use the nitrated specimen, that is as-built condition or either age plus nitrated condition. But we need to choose these, one of these two conditions, that is either we need to use as-built plus nitrated or age plus nitrated condition. So we will eliminate the age plus nitrated condition because for the aging process, we need to further input
30 seconds.
the electricity in terms of kilowatt hour, and that will cause the production of the CO2 gases, SO2 gases, and NOx that can directly harm our environment. Thank you.
Thank you. So with that, we are done for the day. Thank you for being such a good audience. Hope the presentations were informative as well as enjoyable. The results of this will be told tomorrow in the concluding session. So yeah, you can proceed to dinner.